Welcome to another Mathologer video. Most of you will have heard of mathematical superhero Carl Friedrich Gauss, and many of you will be familiar with the great story of Gauss as a schoolboy. Gauss's teacher, so the story goes, had asked the students in his class to add up all integers from 1 to 100. So a tedious task to keep the little monsters busy, but Gauss surprised everybody by blurting out the answer pretty much immediately. And in doing so, Gauss announced to the world that a great thinker was emerging. The story featured prominently in a recent German movie, Die Vermessung der Welt, Measuring the World. That's a screenshot over there. Check it out. It's a great story, and it's even sort of true. But how did Gauss do it? Well, although hundreds of retellings of the story, including the movie version, suggest one particular method, it turns out that nobody knows for certain what Gauss did. In fact, there's a number of details of the standard story that are probably fictional embellishments. Check out the fascinating story behind the story in the article by Brian Hayes, linked in from the description of this video. Great stuff. Gauss's story also has a sequel, well, I guess a prequel, since it happened before Gauss was born. The prequel involves another famous mathematician, Jacob Bernoulli. In his book Ars Conjectandi, Bernoulli boasted that he was able to find the exact sum of 1 to the 10th power plus 2 to the 10th plus 3 to the 10th all the way up to 1000 to the 10th power. And he was able to sum all this in just 7.5 minutes. Think you could do it? Give it a try, with or without a calculator, and let us know in the comments how you go. And if, incredibly, you somehow finish and you want to check, here's the answer. Whoa, what a monster. And 7.5 minutes by hand? Oh, and by the way, notice the remarkable symmetry present in this number? What's the explanation for that? Again, let us know in the comments if you come up with anything worth sharing with the world. Now, two great stories about our two great mathematicians, both in possession of some magic trick to simplify a painful sum. But Gauss and Bernoulli are not alone in this. The quest to find tricks and formulas for sums of powers of integers has been going on for millennia and is still ongoing. There have been contributions by many great mathematicians, including Archimedes, Euler, Pascal, Bernoulli, Ramanujan, Riemann, and many more. What I'd like to do today is to take you on another magical mathological journey. With nicely animated derivations, I'll show you how to discover many spectacular power sum formulas and computational tricks. My ultimate goal in all this is to chase down the famous Bernoulli numbers and the infamous Euler-Maclaurin summation formula. The Bernoulli numbers are a very strange sequence that is at the heart of all the integer power sums. Yes, Bernoulli numbers even lead to that notorious -1/12 weirdness. And the Euler-Maclaurin summation formula is a mathematical mega-weapon. The formula allows us to go way beyond sums of powers to magically calculate very general finite sums. One of the most important, beautiful and applicable formulas in mathematics, and a formula that only the experts tend to understand. Until today. Just wait. As you've probably already guessed, this video is another challenging Mathologer masterclass. Anyway, the usual rules apply. The video is split up into chapters, 8 chapters in total today. We'll start with some really easy stuff and then proceed to ever more crazy and deep stuff. And a warning, today the crazy and deep stuff is even crazier and deeper than usual. But as usual, give it your best shot. Follow as long as you can, and it's fun, and don't worry if you don't get every detail in the first viewing. We'll start with an easy one. So, how did Gauss sum the numbers from 1 to 100? Well, as I confessed, we don't really know. But there are a few things Gauss might have done. There are a few different ways to see the answer pretty much at a glance. Now, to try to keep everybody entertained, including you know-it-alls who are very familiar with this sum, here's a nice and natural method that may be new to you. Let's first add 1 plus 2 plus all the way up to 10. we can represent the sum as a triangle like this. 1 plus 2, 3, 4, 5, 6, 7, 8, 9 and 10. So the question is, how many little unit squares are in this triangle? Or, what is the same, what's the area of the triangle? And that's easy, right? For probably the millionth time in our life, we go base times height divided by 2. So 10 squared, that's 100, divided by 2, that's 50. And that's our sum, right? Nope. Close but no banana. Why? What went wrong? Of course, the problem is that our step triangle is not truly a triangle. That 50 we calculated is actually the area of the genuine triangle here. We failed to account for these 10 half squares, whose area is, well, 10 halves, which is 5. So the answer to our question, the sum we are after, is 50 plus 5 equals 55. And what about the sum from 1 to 100? Of course, it's the same thing, just a bigger triangle with one more 0 everywhere. 100 squared, that's 10,000. Half that is 5,000. Half of 100 is 50. And so our answer is 5,050. And however you got there, that would also have been Gauss's answer. Applause for one very smart little kid. It's now also easy to see that in general, if we sum from 1 to any integer n, we get this formula here. N squared divided by 2 plus n divided by 2. Very pretty. Just simplifying a bit more, this formula can also be written like this. N times n plus 1 divided by 2. I suspect many of you have seen this formula before. Anyway, we're just warming up, right? Okay, what about the sum of the squares? Can we do something similar? Well, just like the sum of the integers corresponds to a stepped 2D triangle, the sum of the squares corresponds to a stepped 3D pyramid. 1 squared plus 2 squared plus 3 squared all the way up to n squared. And here is our complete Mayan-style pyramid. Our new sum, the number of unit cubes in the stepped pyramid, is approximated by the volume of this proper square pyramid. There. Then, dusting off the mental cobwebs, we remember that the formula for the volume of a pyramid is 1/3 the area of the base times the height. Then the area of the base, that's n squared, and the height is also n. So the volume of our pyramid turns out to be n cubed over 3. Again, this number is not exactly the volume we want, but it's a good approximation. Can we now adjust this volume to obtain the exact formula we are after, just like before? Yes, but it's not very mathologery. It's just not much fun. The method of correction and the resulting solution aren't so pretty. And as far as elegant and exact solutions go, this steppy approach is pretty much at a dead end. Pretty much, but not quite. Before giving up completely, aren't you tempted to take a peek into higher dimensions? First 2D triangles, then 3D pyramids, and so what's next? If there's a Mayan god, the sum of the cubes should be a stepped 4-dimensional pyramid with a 3D cubic base of side lengths n and also a height of n. And this stepped 4D pyramid is approximated by a normal 4D pyramid of the same basic shape, and then the volume of this normal 4D pyramid is n to the power of 4 divided by 4. And you can guess the rest, right? There is indeed a Mayan god, and the pattern is clear. Whatever the exponent appearing in our sum, that number plus 1 will appear in our approximate formula here and here. And so the general formula works out to be something like this. A very pretty and handy approximate formula, and very easy to remember. And does this formula seem kind of familiar? Does it remind you of something? Well, if you know some calculus, it really should. Remember that one? Quick and dirty, what this tells us is that the discrete sum at the top is approximated very well by its continuous counterpart, an integral. Interesting, isn't it? It's the harbinger of a very deep and beautiful truth. It's our first hint of the promised Euler-Maclaurin formula, the culmination of our video. Just wait. I'll now get going properly by showing you very pretty and animated derivations of the exact formulas for these three sums. As before, we'll picture these sums in terms of physical objects: squares, cubes, stepped triangles and stepped pyramids. Okay, here we've got the stepped triangle again, standing for 1 plus 2 plus 3 plus 4. There we get the second one. So now we've got two of them and the steps go away, which is really, really good. Now, the area of the rectangle is 4 times 4 plus 1. Okay. Now, if we had used things up to 5, things would change like this. If we'd added up to 6, things would change like this. And in general, things would look like that. And now we just have to divide by 2, and that's it. Great stuff. Well, we're not quite finished, but let's pause and admire this amazing identity. The sum of the cubes equals the square of the sum of the integers. How pretty is that? And so, for example, 1 cubed plus 2 cubed plus 3 cubed is equal to 1 plus 2 plus 3 squared. Or 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed is 1 plus 2 plus 3 plus 4 squared, and so on. And finally, to obtain a properly compact formula for the sum of the cubes, all we have to do is to plug our formula for the sum of the integers in this. And so we get this. I'm sure you agree, it's all super pretty stuff. And if you'd like to see more of the same, head over to Think Twice, a very nice YouTube channel dedicated to short animated proofs. What's next? Well, the next sum, of course. But before that, let's fill in a hidden gap and ask what comes before. Weird question? Well, 1 plus 2 plus 3 and so on is the sum of the first powers. So what about the sum of the zeroth powers? Easy. Each of these integers to the power of 0 is, of course, 1. And there are n of these, so the sum totals to n. Not earth-shattering or rocket science, but it's cute and it will help us later on. And now we can get on with what comes next. What is the sum of the fourth powers? Well, can we spot any patterns here? Well, all the expressions on the right contain the factors n and n plus 1. And that will turn out to be true for all the higher power formulas as well. What else? Well, let's expand all the formulas. Okay, the terms of highest degree are exactly what we expected from our previous pyramid games. And so we expect to also see this in our next sum, right? What else? Well, those 1/2 coefficients of the next highest term are clamoring for attention. It's a pretty good guess that this will also continue, right? Can you see anything else? No? No? Neither can I. The pattern guessing is pretty much stuck at this point, at least for now. We could now go back to our building blocks to try to produce high-dimensional animated derivations, but how are you with 4D blocks? It's actually a lot of fun and well worth exploring, and I actually went wild with 4D blocks a couple of years ago. But to do this now, I'd have to introduce it to visualizing 4 dimensions. And then there's the 5th dimensions and so on. Fascinating stuff, but too far afield for us today. So instead, we'll do what modern mathematicians do. We'll give up on the fun but crazy geometry and we'll look for a purely algebraic way of proceeding. All right, it's algebra time. But first, let's give our sums short names so that it can fit more of me on the screen. That's a plus, right? What shall we call the first sum? Let's see. Let's go for something super original like S1. Then the second sum is S2 and so on. And remember, there was also that zero sum, which of course we'll call, yep, you got it, S0. Now here's the trick. Remember that the sum of cubes, S3, could be expressed in terms of the sum of the integers S1. There, that one. Similarly, it turns out that we can express any of our sums in terms of the lower sums, which means we can bootstrap our way up to get any sum we like. Now, how do we link the sums? What we need is an identity that connects different powers. And what comes to mind? What famous formulas relate different powers? Well, the binomial identities, of course. There. But after some trial and error, it turns out that instead of the pluses here, using minuses is the way to go. You'll see in a second why. Let me now show you how you can use the fifth power identity at the bottom to derive the sum of fourth powers S4. That seems a little weird. Why look at a fifth power formula if we're interested in the sum of fourth powers? But wait and watch. Those fifth powers will vanish with a really cool trick. Okay, we'll begin by moving those weird fifth powers to the right and everything else to the left. Substitute 1 for x. Okay, now also substitute 2, 3 and 4 for x. Evaluate the simple subtractions on the right. That's 0, that's 1, that's 2 and that's, yep, 3. Still a jumble of coefficients and powers, but here's the trick. We'll add all these equations. First on the right. And there you can see it all telescopes and cancels except for one number. So we sum everything on the right, okay? So these two guys cancel out. These two guys cancel out. These two guys cancel out. And the only thing that's left over when we add up everything there is 4 to the power of 5. Now there's nothing special about stopping at the fourth equation. So let's make it general by summing n equations. Looks like this. Now, what about summing the left sides? Well, let's do this column by column. Adding the terms in this column, we get 5 times 1 to the power of 4 plus 2 to the power of 4 plus 3 to the power of 4 all the way to n to the power of 4. And of course that is 5 times S4. Adding up the second column, we get minus 10 times S3 and so on. Just about there. Remember, we're chasing the formula for S4, but we already know the formulas for everything else here. So we just have to solve for S4, plug in the formulas for S0 and S1 and so on, simplify a little and we'll be done. There we go. Fantastic. Great stuff, isn't it? Now, if you feel bored, by all means, double check my calculation. And what then about a formula for S5? Well, we just rinse and repeat. The 6th power binomial identity will generate a formula for S5. Then we can generate the formula for S6 and so on forever. It's all easy peasy, even if it's a slow step-by-step process. But there's also a super magical way to recast this generating process in a way that gives all the formulas in one go. It also makes a super cool connection with another mathematical all-time favorite, Pascal's triangle. Ready for that too? Well, ready or not, I don't care. Let's go. First, just a quick recap to make sure we are all up to speed. So what we've just done is to begin with all the summation formulas up to a certain point. and we want to derive the next summation formula in line. To do this, we translate a binomial identity, which connects the powers of x, into that other identity that connects our sums. Of course, we don't do this just once, but over and over to generate all our formulas. This means we translate all the binomial identities into identities that connect our sums, like that. Now, starting from the beginning, we can again get S0 from the first equation. There we go. S0 is equal to n. Yes, works. Then we get S1 by subbing this into the second equation. There, sub in and solve, right? Yep, works too. Now we sub the formulas for S1 and S0 into the third equation and then solve for S2 and so on. Looked at from another angle, what we are doing here is solving a system of 5 linear equations in the 5 unknowns S0 to S4. However, there are lots of different ways to solve a system of linear equations. One of the niftiest one is to interpret the system as one matrix equation. If you've never heard of this, just run with this as best as you can. It's pretty visual, so it shouldn't be a problem. Okay, here we go. Here is this matrix equation. Now solve using the inverse of the square matrix in the middle. The numbers you see there are exactly the coefficients in our previous formulas. And we now get the formulas simply by performing the multiplication on the right side. Magic. The first 5 summation formulas just like that. And of course, by using more of our binomial identities to start with, we can generate as many of these formulas as we wish. Magic, definitely. But this very nifty method of generating all our summation formulas gets even more appealing and unforgettable once you've looked at it in terms of Pascal's triangle. That is an integral part of our binomial identities, of course. Here we go. Suppose you're interested in generating our first 5 sum formulas. Then you begin with the first 5 plus 1 equals 6 rows of Pascal's triangle. There, we all know that, right? Strip off the row of ones on the right. Rearrange into a matrix. Decorate every second diagonal with minus signs. And calculate the inverse matrix. And the numbers you obtain are exactly the coefficients in our sum formulas. So in a way, our summation formulas are some sort of weird inverse of Pascal's triangle. I'm excited. Are you? And if you want more formulas, you just start with a larger tip of Pascal's triangle. Well, anyway, I think we can all agree that this is super, super cool and super easy to remember. Okay, now that we know how to generate any number of these formulas, let's get back to pattern spotting. Over there are the first 8 formulas arranged by descending powers of n. We already spotted the reciprocals of the integers in the first column. There, those. And we decided that the second column is most likely to be all 1/2. What about the third column? That looks like a complete mess. So let's focus in a bit more. There. Well, that still looks pretty random, but 2 entries that stick out are, at least for me, 5 divided by 12 next to the 5th sum and 7 divided by 12 next to the 7th sum. That suggests that the number next to the k sum could be k divided by 12. Let's see whether this works. 2 divided by 12, that's 1/6. 3 divided by 12, that's 1/4. Yeah, all works out. And in fact, you can keep on going and it always works out. It's great. So looks like we've got our pattern here. Okay, so we've discovered simple patterns in the first, second, third columns. Fourth column. Well, I'll leave it to you to figure that one out. And the same for every second column from then on. Looks like we're getting there. But the master pattern spotter, the first person to really see the pattern, was our friend Jacob Bernoulli. the 7.5-minute guy. After a lot of playing with the first 15 or so formulas, Bernoulli discovered something amazing. Bernoulli noticed that the numbers in the different columns always appear to depend in a simple way on the numbers at the tops of these columns. Now this sequence of numbers, 1, 1/2, 1/6, 0, minus 1/30, 0, and so on, are named, naturally enough, the Bernoulli numbers. And subsequently, his strange sequence was recognized to be one of the most important sequences in mathematics. But hardly anybody knows about it. Outside mathematics. Okay, here then is the amazing pattern that Bernoulli discovered. As before, we begin with Pascal's triangle. Again, strip off the row of ones, rearrange into a matrix, except this time we don't need the zeros. Decorate all entries in columns with the corresponding Bernoulli number. Juxtapose the formulas for the first 5 sums. Strip away all the coefficients except those in the first column. There. And now magically merge. Whoa. This is Bernoulli's celebrated pattern. Really quite something. Who would have thought that calculating the 2D triangular infinite array of coefficients corresponding to our sums can be reduced to calculating a one-dimensional infinite sequence, the Bernoulli numbers? Pretty amazing, isn't it? Again, what this means is that once you know the Bernoulli numbers, you can straight away write down any of our sums. You can check for yourselves that this pattern really incorporates all the patterns that we spotted earlier. Now here's a page from Bernoulli's book where he talks about his discovery. Up the top are the formulas for S1 to S10. He probably used the last one to calculate that humongous 32-digit sum that we mentioned earlier. Now, even given that formula, to accomplish it in 7.5 minutes is pretty damn amazing. I wouldn't try this. Down there is Bernoulli's version of the formula for Sn. At the very bottom we spot the Bernoulli numbers B2, B3, B4 and B5. And how did Bernoulli prove that his superformula always works? Well, he didn't. He just trusted the pattern to continue. As far as I know, the first to nail it all down with a proof was Leonhard Euler. Anyway, definitely another great way to generate all the formulas for our sums. Of course, what you really need to use this method is a way to calculate all the Bernoulli numbers. But that's pretty easy. Now, before we go there, a challenge here. There's a mistake in Bernoulli's formulas as they're written over there. Can you spot it? Anyway, here's one way to calculate the Bernoulli numbers. The formulas down there work for all n. So in particular, they work for n is equal to 1. Okay? For n is equal to 1, all the sums have just one term, namely a power of 1. And therefore, and since all powers of 1 are 1, all these Sn are equal to what? Well, 1 of course. And now we can solve the system of equations, for example, by using matrices, just as we did earlier. Very pretty. Very pretty, and also very similar to our original matrix solution for the Sns. Right, that one. In fact, using the top formula to find the first 5 Bernoulli numbers is exactly as much effort as finding the Sns using the second formula. Then, to get the Sns from the Bernoulli numbers takes an additional step. And so for the initial goal we set ourselves to find a formula for the Sns, using the second identity, which avoids the extra step, is definitely the way to go. So then, why bother with the Bernoulli numbers at all? Seems way too complicated if all we want is our power sum formulas, right? Right. Except, as I mentioned earlier, the Bernoulli numbers pop up everywhere. They are not only found inside our finite power sums, they also play a central role in hugely important infinite power sums and things like the Riemann zeta function. Ready to be dazzled? So far, this has all been about these sums of positive powers. How about negative powers? Unfortunately, no one knows any simple formulas for these negative power sums. However, extremely interesting things happen if we don't stop, if we add all infinitely many terms. The first sum, known as the harmonic series, explodes to infinity, despite its term getting infinitely small. I've already shown a couple of different proofs of the surprising explosion in previous Mathologer videos. So I've also talked about the second series of reciprocal squares in one of my videos. I showed an ingenious proof by Euler that the sum of this series is pi squared over 6. In fact, Euler used this method to calculate all the sums of even powers. For example, the bottom series with fourth power sums adds up to pi to the power of 4 divided by 90. And after pondering all these even power sums for a number of years, Euler also eventually came up with this very stunning general identity. And yep, those are the Bernoulli numbers there, at the heart of Euler's formula. We'll have to make another video about all this at some point, so I can also talk about those mysterious, unmentioned odd power sums. But that's definitely not all as far as the Bernoulli numbers are concerned. Let's return to the positive powers, ignoring all common sense, and sum to infinity. What do we get? Most of you will have seen at least a couple of the nonsensical pseudo-identities over there. Especially that first notorious minus 1/12 sum. Of course, anybody who knows anything realizes that as written, these identities are ridiculous, since all of these series explode to infinity. Nonetheless, something super interesting and important is hiding behind these identities. First, the numbers on the right are really just Bernoulli numbers in disguise. Secondly, the identities become meaningful when the meaningless left sides are replaced by the corresponding and meaningful values of the famous Riemann zeta function. If this last remark makes no sense to you, you've got another crazy Mathologer masterclass video waiting for you, where all this is explained. Still here? Whoa. Need another coffee? Maybe pause and get one anyway. I gotta warn you, we're about to enter the deep part of the deep end. We're now heading into territory that even many of my mathematician colleagues will know very little of. As always, I've attempted to make the presentation as visual and accessible as possible, but we're pushing the Mathologer boundaries here. Okay, last chance to bail out and go watch another cat video. That's a no to the cat video? Great. Mathematical seatbelts and crash helmets on, and let's go. Now that we have sums of simple powers under control, it's natural to also look for summation formulas for functions that are composed of these powers. Functions such as polynomials, or functions that can be expressed as power series like sine and the exponential function. Now, before we launch into summation formulas, let's have a quick calculus refresher. Let me remind you how to differentiate and integrate these power series functions. That's actually really easy, exactly as for polynomials. So to differentiate such a function, you simply differentiate term by term, no matter whether the sum is finite or infinite. There, to differentiate, the derivative of the aqua is 0, the derivative of the green is C1, and so on. For the second or higher derivatives, just go again. There. Integration is just the same in reverse and also works termwise. So there, termwise, that one, and so on. Ooh, okay. The plus c is annoying here, but we can make it 0 by selecting one particular definite integral, this one here. Maybe pause and ponder this for a moment if this is not immediately clear to you. Anyway, with these preliminaries out of the way, let's do some serious function summing. Let's begin by choosing f of x to be our good old friend x squared. Then remember, we rewrote the summation formula for the squares this way. Now we can write the left side in terms of the function f of x. The 1 squared is just f of 1. The 2 squared is f of 2. And in total we get this. Okay, now if we switch from x squared to x, then s2 on top changes to, well, just s1 of course. If we then change to, well, whatever, x to say 7x, then the right side changes to 7 times s1. If we change f of x to this randomly chosen polynomial, then the right side changes accordingly. All pretty straightforward, right? So let's call our new sum S. Very original again. Now let's cross our fingers, go completely general and head off to infinity. There. And then the sum should be this, right? All okay so far? So to get the summation formula for a finite or infinite polynomial, you just replace the powers of x by the corresponding s's, right? Well, maybe. Maybe. That infinite sum of s's on the right is definitely a little bit of a worry. But don't worry. Be happy and let's leave the demons for later. Now the idea is to express this general summation formula in terms of the Bernoulli numbers. Okay, so first here again are the Bernoulli formulas for the s's. Let's write them top to bottom. Okay. Now connect the s's into the sum we're interested in. So the constants have to go in. Okay. Expand out. Okay. So finding our sum amounts to summing all the entries in all the boxes. And the clever trick is to do this row by row rather than column by column. We started with columns, right? Can you see why this is a great idea? No? Well, let's do it together. First, row 1. Okay, take out the common factor here. Nice. Can you see why? Well, the expression in the brackets is exactly the integral from my calculus refresher intro from a moment ago, evaluated at n, so this guy. Now on to row 2. Take out a common factor. We can simplify this a bit. 1/2 times 2, that's 1. 1/3 times 1, that's 1. So everything goes away, right? Okay, and now the sum in the bracket should be familiar, right? So there we've got a bit of a coincidence. Yep, the sum in the bracket is exactly f of n except for the missing c0, which means we can write the bracket like this. Almost done with row 2. Just one more nice insight worth incorporating. Evaluate f of n at 0. That wipes out pretty much everything on the right. Okay, so c0 is just f of 0. We'll substitute that above and row 2 is done. On to row 3. Well, I mean, you know the drill. Take out the common factor and looking carefully again at the bit in the bracket gives this. Consider filling in the details as your homework assignment. Involves fiddling a bit with binomial coefficients, but shouldn't be much of a challenge for you calculusy guys out there. Anyway, the pattern that emerges at this point continues to infinity. And that's the infamous Euler-Maclaurin summation formula. Great, isn't it? We've turned an everyday finite sum into a truly infernal infinite sum. Not obviously so great, but don't worry. I'll conjure up some mathematical magic that will convince you it's a great formula. But before we apply the formula, let me fiddle with it a bit. This will highlight the hidden parts of the underlying pattern and will present the formula in its most useful form. To begin, it often makes sense to replace lots of derivative dashes by numbers in brackets. So those 2 dashes get replaced by 2 in a bracket. This one here gets replaced by 1 in a bracket. But the function values in the b1 term involve 0 derivatives, and so the pattern fits this line as well. There. And why stop there? The integral in the b0 term is an antiderivative, which is exactly a -1 derivative. So we can write the first term to fit the same pattern. Very pretty and slick, don't you think? Okay, very pretty, very slick. However, when we actually apply the formula, it turns out to make more sense to use a version of this formula in which this pattern is only partly visible. So let's start again with our original Euler-Maclaurin formula and fiddle with it slightly differently. Okay, b0, that's just 1. And b1, that's 1/2. Okay, right like that. Leave b2 for now because the next one's easy. b3 and all the other odd b's are equal to 0. And so we can simply zap all the corresponding terms. Now come a few more cosmetic twists and turns that morph our formula into this form. Can you spot the differences? Well, I'll give you a moment. Okay, countdown. 3, 2, 1. You got them all? Well, here they are. All the zeros here turn into ones over there. And the minus sign here turns into a plus sign. Maybe try to justify this final morph yourself. It's actually a little trickier than it looks. Also, just in case you get stuck and desperate, I'll indicate the argument in the description of this video. Fantastic. But what is this fancy formula good for? Again, it seems pretty crazy to turn a finite sum into an infinite sum plus an integral. Well, the Euler-Maclaurin formula can be used to evaluate or approximate tricky integrals in terms of sums and the other way around. Very technical mathematics, but incredibly powerful and beautiful. To do justice to this magical formula, I should now spend an hour or so showing the formula in action. Applications to the Riemann zeta function, like justifying the -1/12 bit, Stirling's formula for approximating factorials, the Euler-Maclaurin constant, and so on. But another hour may be pushing my welcome, so I'll save the full Euler-Maclaurin extravaganza for future videos. However, let me finish this video with just one illustration, an amazing power summation story. Following little Gauss and not so little Bernoulli, it's now Euler's turn. One of Euler's amazing and most famous achievements was the solution of the so-called Basel problem, the evaluation of the sum over there of the reciprocals of squares in terms of pi. While working on the problem, Euler first numerically calculated the sum and many related sums to 16 plus decimals. Here are 2 pages from one of Euler's books where some of his approximations are shown. So given this approximation, Euler first seems to have guessed the exact value to be pi squared over 6. Yep, Euler was that kind of guy. So you look at this and you guess this is pi squared over 6. I wouldn't have guessed it. Pi squared over 6, that's the bit in the green box. But how does one calculate a good approximation of this infinite sum before knowing the sum is equal to pi squared over 6? Well, easy, right? Just add 1 plus a quarter plus a nines and keep going until you get sick of it, right? Wrong. The trouble is that this infinite sum converges very, very slowly. For example, summing the first 9 terms gives this. Not even close. In fact, to get those 16 correct decimals that Euler found, you'd have to sum around 10 quadrillion. That's 10 to the 16 terms. And although Euler was a very stubborn man, he wasn't that stubborn. This is simply an impossible task to do by hand. And might be even really, really hard with a computer. To do the impossible anyway, Euler unleashed the Euler-Maclaurin formula on his problem. Okay, now if someone tells you that this formula is the solution to our approximation problem, what function would you choose? Well, we're adding the reciprocal squares, and so f of x equals 1 over x squared is of course the natural choice, right? And luckily 1 over x squared is a nice polynomial power series thingy, and so well, of course 1 over x squared is 100% not the kind of nice function that we had in mind when we derived the formula. But no matter, let's cross our fingers, pray to our Mayan god, go on autopilot and see what happens. So, writing out the formula with f of x is equal to 1 over x squared, well, that's just baby calculus, and here is the result. Ignoring the dodgy equal sign, what have we got? Well, there's the sum of constants here, plus this sum of terms that depend on n. It's easy to get the yellow sum under control, at least in the cavalier manner that we're using here. Just let n dash off to infinity, then the finite green sum on top turns into the infinite sum we're interested in. And all the tiny terms in the aqua sum vanish. Like for example, 1 over n, if you let n go to infinity, that goes to 0, right? Cool. So the yellow is apparently equal to the infinite sum of reciprocal squares above. Back to the full equation. There. So we can replace the yellow sum by the infinite sum of reciprocal squares and rearrange the equation like this. Solve for the yellow infinite sum we're chasing. Yeah. Okay. Now chop off the infinite sum in the aqua after a few terms. There. This should give an approximation of the yellow infinite sum. Now, fingers and toes and everything else that we haven't crossed yet, crossed. Let's see what happens when we compute this approximation for a small number like n equal to 9. Remember, the green sum alone gives a pretty terrible approximation to the full yellow sum, correct to like 0 decimal places. And what if we include the aqua? Well, believe it or not, the new approximation gives the correct answer to a whopping 8 decimal places. What if we wanted Euler's 16 decimal places? Well, it turns out n is equal to 9 will do it with just 6 more of the aqua terms. Real mathematical magic. Instead of having to add quadrillions of terms of the series, Euler gets away with just 9 terms of the series plus a few correction terms conjured up by his formula. I glossed over a ton of very interesting and tricky technicalities, appealed again to the gods, and some really crazy stuff that makes all this even more amazing. Anyway, I'll be back to give you more Euler-Maclaurin magic. I promise. Let me just mention one final super crazy fact. Having seen Euler's magic, you might expect that by adding more and more of those aqua correction terms, we could approximate the infinite sum as well as we like, to any desired accuracy. However, this is not the case. In fact, for fixed n, like our n is equal to 9, the aqua sequence actually diverges. To start with, you get better and better approximations, but then, from some point, adding in more of the aqua makes the approximations worse and worse. How weird is that? And why does this happen? Well, as I said, this won't be the last video featuring the Euler-Maclaurin formula. There's just so much good stuff here. If you'd like to play a bit with the Euler-Maclaurin formula, you could try to replicate some of Euler's 16-digit approximations. Or you could unleash the formula on x squared or some other positive power of x to see how the Euler-Maclaurin formula turns into the familiar sums. Or make yourself famous and discover a nice pi-based way to express the sum of the reciprocal cubes. That second entry in his list even defeated Euler and is still defeating the greatest mathematical minds today. To finish, here's an animation of a second glorious proof of the sum of the cubes that I ended up putting together while working on this video. You've well and truly earned it, plus at least a cat video or two. And the world needs to see this one as well. Oh, and can everybody who made it all the way to the end please give some feedback as to what did and didn't work for you and what your background in maths is like. This would really be helpful to know in my quest to get away with ever more insane videos. Okay, that's it. Bye for now and enjoy the movie.